right, so we've talked a bunch about rate laws. And we know so far that a rate law has to be experimentally determined. And we looked at some experiments and we got some rate laws and everything was fabulous. During the course of our conversation about rate laws, we did talk about the fact that most chemical reactions don't happen in one step. Most chemical reactions happen in a series of steps whose overall reaction, if you added everything together, would be the balanced chemical equation. Are you with me there? Okay. The series of steps is called a reaction mechanism. So a reaction mechanism is the step-by-step sequence of elementary reactions, elementary steps by which the overall chemical change happens. So you can think of an elementary reaction as a baby step. And you know what? You've already worked with elementary reactions when we did Hess's law. Remember Hess's law? Where you had a bunch of reactions, 5 or 6 different reactions, and flipped them around, you multiplied them by a number, you divide them by something, until they all added up to the target reaction. Those baby steps are exactly the same as these baby steps.
Wait,
right.
So the entire thing for Hess's law is baby step, or each individual line is baby step?
Each individual line was the baby step, and the overall chemical equation is the target equation, the thing you're looking for. And that part is the same here as well. Now, a reaction mechanism is somebody's idea of how all those baby steps fit together. So when somebody's thinking, I wonder how we get the reactants to go to the product, I think it goes in this series of steps. And the guy writes it down, or the woman writes it down, and they say, okay, this is what my hypothesis of the mechanism, the steps involved in making this balanced equation. In order for that mechanism to be considered valid or right, these two conditions have to be met. First of all, the sum of all the elementary steps must give you the overall balanced equation. That makes sense. And the mechanism, the rate law of the mechanism must agree with the rate law that's been experimentally determined. So here you
it's
go.
just Hess's law?
No, hang on. So you have to make sure that all your steps add up to the balanced equation, and you have to make sure that the rate law that they found in the lab agrees with the mechanism rate law. Okay, one more time. An elementary step are the pathway reactions that add up to the target reaction. If you wanted, you could write a rate law for every single elementary step, and it's written from its molecularity. Do not be afraid of the word molecularity. It's scary. You don't know what it means, but it's easy to figure out. Okay? This is the only time where you're going to look at a equation, right, the form of the rate law that you're aware of from previous work, and you're going to use the coefficient as the order. The coefficient becomes the exponent. This only happens when you're talking about an elementary step. The one and only time. No coefficients when you're looking at the overall reaction. Okay. All right, and the molecularity is the numbers of species. Do you know what species means when we're talking in chemistry?
No.
Nope.
It's after genus,
Chemical.
right?
Just chemical. So the number of chemicals that must collide to produce the reaction that you're looking for. If you have a molecularity that is unimolecular, that means one. That means a reaction involving just one molecule. Look, here's one that's unimolecular. Remember, we don't care about the products at all. We're just looking at the reactants. And A decomposes to some products. That is unimolecular, and the rate law that is associated with this elementary step would be the rate is equal to the rate law constant times the molarity of the reactant raised to whatever the coefficient is. Remember, chemists are lazy. They never write one. There you go, just for you. Now, if this elementary step has these two things colliding in order to make a reaction, that would be bimolecular, and the rate law would be equal to the rate law constant times the reactant. Both reactants are A, based on their coefficients. 1 plus 1 is 2.
So molecularity isn't anything like molality or molarity?
No, not at all.
Okay, good.
So if you have a species called A and a species called B, and they need to collide in order to have a reaction, that would be bimolecular. The rate law would be K times the concentration of A and the concentration of B. These I can see happening. You need to get the, remember our collision theory, you need to get these lined up properly with sufficient energy. What else?
Right.
The orientation. Okay, better look that up. Now, there is such a thing as a termolecular, and the rate for that would be K equals A times the raised to the third power. And you can see as we go on. These are very difficult to get 3 species or 3 reactants to collide simultaneously in the correct orientation with the effect of in the right place and with the right frequency.
So, if these are just things colliding, how would A collide with itself? Like in
This one
in
is
unimolecular?
decomposing.
Oh, okay.
Okay. All right. Now I'm going to talk about some vocab that's not going to make sense until we are almost done. An intermediate is a species, a chemical thing, that's neither a reactant nor a product. It is formed and consumed during a chemical reaction. When you see one, you can tell what it looks like. Now here is the rate determining step. All mechanisms have a rate determining step. It is the slowest step in the reaction mechanism. It is the slowest elementary reaction, and it determines the rate law. Here you go, write yourself a little note. Write the rate law from this step. All right. When I first started working at this school, Telge was a 2-lane highway. It wasn't that long ago that you got that wrong. Telge's only been a divided highway with a median for about 3 or 4 years.
Oh, he's a highway.
Telge's only been a divided road for about 3 or 4 years. Now, when I drive to school, I like to drive down Telge at about
90 miles an hour.
75.
That's fine.
Is that a confession of guilt?
No. But it is a nice visual. Okay,
30
everybody,
miles.
ready?
Oh,
Here
I
I
get
am.
where this is going.
Driving down the road. All right, now, in my kitty car. Now, when I was driving on that 2-lane highway, it was under construction all the time. There was a lot of people coming the other way, so I really couldn't pass. Even though my speedometer goes up to 180 miles an hour, I couldn't pass because there was always a car there. I do not have a flying car. So I would be stuck very frequently behind this lady that apparently had no place to go. And she would chug down Telge at about 25 miles an hour. How fast could I go down Telge when that lady was driving?
25.
25 miles an hour. That is it. She determined how fast I drove down Telge because she was slow.
She was the limiting reactant.
She was she was the rate determining step.
That too.
Rate
She was
determining
both. I have
step.
I have a question.
Okay, hang on for a minute, okay? So no step can go faster than the slowest. All right, here's another vocab word for you. A catalyst, that I'm sure you remember from biology, is a chemical thing that's present in the first elementary step as a reactant and the last elementary step as a product. It must look exactly like that. Do not get it confused with an intermediate.
Would they usually have like a name for it, or would they put a
I'll show you a number of things about it later on, okay? A catalyst speeds up the rate of reaction. Sometimes we use an inhibitor. In the rate mechanism, it looks exactly the same as a catalyst. It's present in the first elementary step as a reactant and the last elementary state as a product. The deal with an inhibitor is that it slows down the rate of reaction.
The old lady was inhibiting the work.
Yes, yes. Well, she was kind of, all right, whatever.
And if she got scared
No,
by
she
you
was
driving and
determining
drove
her rate.
faster, you'd be the
Come on,
catalyst.
man.
Okay, here we go. Let's look at this small example, and we can go ahead and define some terms when we look at this. Okay, here is a reaction and this is the overall reaction. Write that down. The overall reaction. 2A plus B yields D. Somebody thought, I think that it occurs this way. I think that A and B collide and they form C. This happens kind of slowly. And then the C that's formed reacts with some A to form D, and I think this happens fast. Now, there are a couple of things that we need to check out in this, and this is what I want you to do. For step one, the first thing I want you to do is look at the reaction mechanism and find the rate determining step. Which one is it?
Step one.
Step one, mark it, rate determining step, RDS. The next thing you do, once you find the rate determining step, is you write the rate law from it. Remember, rate law always comes from the slow step. The rate law would only take into account the reactants. This is a bimolecular, so the entire rate law has a second order. So the rate is equal to the rate law constant times the concentration of A times the concentration of B. This is second order. There's one on each one of these. Now, once you've written the rate law, you go ahead and check the overall reaction, the overall equation. And you do that by adding up all the steps. So when I look at this,
A squared.
I'm
plus B.
looking for the presence of a catalyst. Do I have one?
No.
No. I do not see a reactant in my first step that's a product in my last step. There is no catalyst and there's no inhibitor. Is there an intermediate?
Yes.
Yes, there is. An intermediate is neither a reactant nor a product. It is something that is formed and then consumed, so we can cross it out. So the overall reaction here is 2A plus B yields D. Okay. Now, this is what I'd like you to write on your paper. Here's a procedure for dealing with rate mechanisms. The first thing you need to do is determine the rate determining step. Find it. Second thing I want you to do is write the rate law from the rate determining step. Third thing is to write the overall reaction. And when you write the overall reaction, you are going to cross out intermediates. And you're going to note any catalyst or inhibitor. And I'll show you how to do that in a minute. Okay. All righty then.
Wait,
Yes.
we still need to count down 3.
Okay. I would like you to, I'm sorry that this got rolled over on another page. Here are the elementary steps, and the questions are on the other page. Do A through D, please. Here are the procedures.
So I think the slowest step, we read the rate law from it, but wouldn't the other steps still take time? So
They do, but the whole rate cannot go any faster. Yes, it does take time.
yeah,
But remember what the rate is, the change over time, not time,
yeah.
not the time involved. We want to see what the change in time, the change in concentration per minute time.
No, but like if one reaction took like half a second and it was the slowest process, but the other one took like 0.49 seconds, it would still take,
Yes, it still takes time.
Let me know if you want me.
Okay, you got, you have to think carefully about what rate is.
Yeah.
Okay. Okay. Because I'm filming this, I'm not going to give you time to do it, so just watch, okay? All right, so your procedure says determine the rate determining step. Which one is it, 1, 2, or 3? 1. There we go. Let's write the rate law right now. Rate is equal to K NO raised to the second power. Remember, this is an elementary step, and in an elementary step only, the coefficient becomes the exponent. Now, we can go ahead and write the overall reaction. Before I do that, I would like to see, do I have any catalysts or inhibitors?
No.
Nope. Do I have intermediates? What are they?
N2O2.
N2O2. It appears it is formed and consumed in the same reaction. Any more?
N2O.
N2O. Formed and consumed. They're gone. Okay. So our intermediates are N2O2 and N2O. Our overall reaction then would be these 3 steps added together. 2NO plus 2H2 yields N2 plus 2 H2Os. Good?
Yes.
All right, moving on. And so we answered all of this stuff. All right. This reaction mechanism asks us to write the overall reaction and what is the catalyst and how do you know. So they kind of like spilled the beans. There is a catalyst. What is it? H plus. It appears as a reactant in the first step, and it is a product in the last step. So I want you to circle it to remind yourself that it is a catalyst, and we do something special with the catalyst. Hang on for a minute. Any other catalysts? No. Any intermediates? This one, CH3CH2OH2 with a positive 1 charge is the same as this,
CH3CH2.
this, and this. Is that it?
Yes.
All right, the overall reaction will be the, when you add all of these together. CH3, CH2OH. The catalyst is conveniently written above the arrow that signifies this is a catalyst. It's neither, it's not consumed in this. All right, and then,
Plus just a proton.
yeah, so what they did was acidify the solution. So CH2CH2 plus H2O.
How would you
Since they-
add just a hydrogen ion to the solution?
Well, you don't add just a hydrogen ion. You add a strong acid that dissociates completely, furnishing a hydrogen ion.
Why is it
ignoring what would've gone with it?
CH2 rather than C2H4?
It's an organic compound. What?
Are we assuming it's catalyst since it says fast on all of them?
No, actually. There is a way to figure out which one is a rate determining step, but we don't want to do that right now. And it's beyond the scope of this class.
No, isn't that why it's not an inhibitor?
It could also be an inhibitor, it's just.
But since it never slows
It's
down.
because they're
Oh,
all
I see.
fast.
How you know it's catalyst versus an inhibitor.
They're all
Yes.
fast.
Yes. Okay. This, depending on what form of word the copy lady, and it wasn't any form of word I had, so it's formatted so badly, I'm just going to omit it. It's not helping us out here. Okay, we're going to come back and do this
Bless you.
after I finish filming. I am going to leave this, which is tricky, until Monday when you're very fresh and ready to go.
Sounds good.
Yeah, Monday. Be careful, Monday, you're getting a, you're having a work day. And on Monday, you're working on a worksheet called Wicked, so just keep that in mind. Okay, I want to talk about catalysts a little bit. Now, a catalyst is defined as a substance that speeds up a reaction without being consumed. Okay, it works this way. This is really important. Please pay attention to this. It lowers the activation energy of a reaction, but it does not change the delta E or delta H, same thing, the enthalpy of a reaction. This is how it works. So here we have the reactants, the transition state, and the products. You know, the activation energy is the amount of energy from the reactants to the activated complex or transition state, the very tippy top. The reaction must have enough energy to surmount the activation energy before the products can be formed. A catalyst lowers the activation energy. You'll notice that the energy of the reactants and the energy of the products remains the same. Guess how an inhibitor would work.
Raise the other way.
Right, it would exactly the other way around. It would raise the activation energy. All right. It works by providing alternate reaction pathways, maybe a elementary step that's different. And it results in a higher percentage of effective collisions. They don't talk about catalyst much on the AP exam. They will next year, but this year they're not going to. The only thing that I want to talk to you about is what's meant by a heterogeneous catalyst and a homogeneous catalyst. A heterogeneous catalyst is a catalyst that's in a different phase of the reactants. A lot of times they will use a piece of metal as the catalyst, that serves as a catalyst. It's a place that you can have the reaction on. And what it does for you, I don't know, maybe it provides mobile
Plus you can
electrons
Plus,
to make things move. You know what? It's irritating the absolute fire out of me. If you don't want to be here, you want to sleep, go someplace else. All right. So it is in a different phase than the reactants. A homogeneous catalyst is in the same phase as the reacting molecules. Catalysts are hugely important in biological systems. Hugely. Because you know what? You can't just like you have all sorts of chemical reactions happening to you all the time. We cannot speed up the rate by heating you up, correct? No, you can't. You
I
have
try.
a very, very small and limited temperature range at which you can survive. 106 and you're done.
isn't it like also 86 and you're done?
Oh, I don't even think it's 86. I think you are degrees.